All right, good morning or afternoon or evening, everybody. Let's go ahead and take care of Explore 4. Okay, I'm going to draw our notes out right now. This is the last Explore page for the Newton's laws. Go ahead and write down the date that you are writing these down. It happens to be November 22nd this morning when I'm writing this down. I'm going to write our template, and we'll go ahead and just take the essential question, provided do action and reaction forces cancel out? Cancel. It should be a C, cancel out. Question mark, okay? And I think that the opening sentence in the paragraph is maybe kind of a good guide for us. Since action and reaction forces are equal in magnitude and opposite in direction, it is tempting to think that they can cancel out. However, they do not. Consider the diagram and note which objects the action and reaction forces act on. The action force acts on the nail, while the reaction force acts on the hammer. Okay, for some reason my pen is not writing on the text, but my finger is. So, interesting. Let me see if I can. Okay, well, I'll figure out how to do this here. Okay, so in the picture here, I'm going to go and put down Roman. First off, write what you know, okay? What I know. Or, remember what I said, or think, okay? So sometimes I see you guys write that you know nothing, and I'd still like you to think. So what do you think about this topic, okay? Hit pause, write it down. All right, coming back to our example here. They give you the example of a hammer, right? And maybe you want to draw this down. Hammer kind of looks something like this, right? And it has we'll call this the hammer. And you have a nail, right? And we'll go ahead and draw a nail. This is the nail. And what we have is we have the hammer is going to hit the nail with a force. That'll drive the nail into a piece of wood, for example. And the nail is going to hit the hammer with an equal and opposite reaction, right? You can see and we could say that this is the action force, right? We could say this is the action force. And we could say that this one was the reaction force, right? Action, reaction. Because action and reaction forces act on different objects, okay? So what I'm doing right now is I am going to, I guess, use my finger. They do not cancel out because they're different objects. Equal and opposite force cancel out only when they are both acting on the same object, okay? So let's write down a little qualifier here, okay? Because this could be a confusing aspect, okay? In this case, we have two objects. Object number one, and we have this one, which is object number two. They don't cancel out. Okay, versus if you remember from our box example, remember when we had a box and we said that somebody could be pulling on the box with a force of 2 newtons that direction, and somebody could be pulling on the same box but 2 newtons in the other direction, right? This would basically be your negative 2n, and this would be your positive 2n if we want to use that. In this case, the forces cancel out. These two forces are acting on the same object. There's only one object in this picture, the box. These two forces are acting on the same object. Therefore, they do cancel out. They cancel out. Okay, and they're canceling out because they're equal in magnitude, right? This is a plus 2 plus a negative 2, right? The plus 2 plus a negative 2 equals 0. It cancels out. Okay, so that's good. At least we've talked about that, and now you just kind of have to think about that for a while. Okay, so let me see if I can clear my screen here, and let's see if we can continue to move on here. Okay, Newton's third law. For every action, there's an equal and opposite reaction. That is what we're talking about. And that is what we talked about in Explore 3's notes, right? Let's go ahead and maybe this should be B. Okay, I don't know if this was an A, if we made an A here, but might as well go make this A, okay? And B, Newton's third law. Is universally true for all forces and in all circumstances. Okay, and there's quite a few different kinds of circumstances. This can be applicable when we're talking about gravity. It's so weird that that thing doesn't want to. It works with gravity. Okay, when you have two objects that have mass, say the moon and the Earth, the Earth and you. Gravity is going to be an attractive force that pulls both of you together. You will accelerate noticeably because you have such a small mass. The Earth will accelerate in a way that you and I can't even appreciate because the mass is so large. So this works for gravity and gravitational forces. This also is going to be applicable when you talk about acceleration. Okay. And so make sure you understand acceleration. We talked about that the other day. A change in velocity over time. Anytime an object changes speed, you have acceleration. Anytime you have an object that changes direction, you have acceleration. Okay. So what do we want to say for Newton's third law over here in our notes? Applies or is applicable, applies to many situations, right? I.e., let's see here if that was. It applies to gravity and gravitational force. It applies to sorry about that. Clear the screen. Go down here. As you can see in this paragraph, Newton's third law of motion applies to gravity. It is also applicable to electrostatic forces. Okay. Electrostatic forces. All right, so that's pretty good. Make sure you got that. So we're talking positive and negative forces right here, right? And let's kind of go back up here, scroll back up here just a little bit. And we had kind of drawn your attention to some of the concepts here about acceleration. So we're going to go ahead and add that into our notes here, okay? So again, this is just a little refresher information. Number 2, second law of force equals mass times acceleration. Make a note that force is directly proportional to acceleration, right? It's also directly proportional to mass. We want to make sure we understand that acceleration was a change in velocity over time. Okay. And we want to make sure that acceleration can change with changes in speed and direction. Okay, these are both circumstances where acceleration can change. Okay, and we also, again, a little bit of review, we talked about the acceleration due to gravity. Due to gravity, and we're talking about near, remember, on Earth, near Earth's surface. And that is equal to 9.8 meters per second squared. Okay, these are just some numbers that we've dealt with, we've talked about, and we just want to make sure you have a pretty good understanding of it. Okay. Also in the video, I guess there's a lot of things we're just kind of adding here. Don't forget that when you're calculating the force of gravity between two objects, and this is why you have a mass 1 and a mass 2, force between two objects, then that formula was going to be the gravitational constant times the mass of object 1 times the mass of object 2, and that was all going to be divided by the distance between them squared. Okay, and this again was your gravitational constant. Okay, which was 6.67 times 10 to the negative 11 newtons times meters times kilogram per second squared. All right, so, and we've already taken that in our notes as well. All right, so kind of moving down, make sure you're reading the text. It kind of flushes out these ideas. I'm right now just trying to make sure that we pen in our notes the main ideas, okay? So if we talked about this idea here a little bit, electrical forces, then we're talking about positive versus negative forces, right? And the magnitude is the amount of charge, like you charging up a battery, and the longer you let it sit on your charger, the more electrons it builds up inside, right? So that's the magnitude, is the amount of charge that's built up in there, okay? So when 2 points charges are placed by each other, they experience an attractive or repulsive. So that's probably also worth just kind of making a little note to ourselves there. This chapter is not on electrostatic forces, but these can be attractive or repulsive. Okay, these can be attractive or repulsive forces. Um, all right, so you're going to actually see some videos in here. And in the future, we're going to dive into this with greater detail, but videos on Coulomb's law, which are going to mirror uh, these equations, some of these equations that you're seeing. You're going to have some additional reading passages that we really, of course, recommend you watch or read. Okay. And it looks like the last topic that we're going to talk about here in our notes is just examining friction a little bit more. So let's go ahead and do that. This will be, I guess, letter C. Okay. Probably need to draw our line down here a little bit. Okay. Do that. This will be capital C. Okay, and so let's just go ahead and title this one Friction. And what can we say? Friction is the force that opposes the momentum of an object as it moves. Okay, it is proportional to the normal force, and it is exerted in the direction opposite to the direction of motion. And friction is caused by the rubbing of two surfaces. All right, so let's put down here, number one, friction is caused by the rubbing of two surfaces. This is why you can snap your fingers. You snap your finger, and the thumb and your middle finger are going to have friction between them as they rub against each other, and that's going to produce that snap sound, right? Maybe you buy particular shoes so that you can have more friction with the ground. If you're a basketball player, you are interested in good friction, right? You want that traction on the wood table, or you want it on the wood floor. There's other times where you maybe do not want to have a lot of friction, and you would not be interested in having that traction. Maybe you're an ice skater and you want a blade that has very little friction so that you can actually roll on the ice nicely, right? So, all right, so that's number one. Let's put number two here. Friction is the force that opposes the momentum of an object. And remember, it's going to be an opposite, right? In the direction opposite to the direction of motion, opposite to the direction of motion. Friction is caused, and then we already said that part. Okay, good. So in this whole paragraph, they were basically talking about how your floor can get scratched up when you drag something across the floor. Well, obviously, based on what you've read and what you know, that's a result of friction. And what is interesting is you scratching the floor is actually what they call displacement. You are actually displacing material from the floor surface. When you take a look at the friction of a glacier rubbing on a rock surface like Earth, uh, if there's enough mass, that's going to produce um, enough downward force on the rock that it's going to displace some of that rock surface and etch it or scratch it out. Okay. All right. So it looks like at this point you're going to have some homework problems, but these are the notes for you guys. So let's go ahead and wrap it all up with a summary. What I'm going to say here. Oh my gosh, sometimes these pens, a summary sentence, okay? So go ahead and just write that out for yourself, okay? And you'll be done. Summary. Let's not make a summary sentence, let's make it a summary paragraph, okay? So, to try to give me about three sentences, just kind of summarizing what you've learned here. All right, you guys have a great day. We'll talk to you soon. Bye-bye.